Now we will look at the mathematical method to represent the motion. Okay, we use the kinematic equation to represent the motion. So far we use the graphical, the graph, representation of motion by the graph. So using representation. Anyway, maybe the most useful and this is the most way that we will use to represent our motion, to represent the motion of an object, is to use the mathematical way. And we use it through the kinematic equations. Okay, first I will introduce you the equation without the derivation first, and at the end of this chapter we will derive these equations using the calculus technique which we will use throughout our study. First, this is the equation for the velocity. All of the equation in this chapter is under this is the motion under constant acceleration. Okay, this is a motion under the constant acceleration. And the equation of the velocity is this equation. In this equation, we assume that the initial time ti is 0, and we use the t as the final time, and we have this kind of equation. For constant acceleration, we can prove that the average velocity is equal to the initial velocity plus final velocity divided by 2, or it is a half of the summation of the initial and the final velocity. Okay, we can show this using the kinematic equation. Okay, third equation is that this, in fact, this is the equation, or this is the definition of the average velocity. Okay, since the average velocity is equal to the final position minus the initial position, or this is a displacement divided by final time minus initial time. So this is the definition of the average velocity. So if we do a little algebra, we can change the equation to this form, and again we use TF as T, and Ti is 0. Okay, so we have this kinetic equation, number 3. Number 4, maybe this is what we are all familiar. This is the equation that describes the final position of the object. In terms of the initial position, the initial velocity, the constant acceleration. Note that the acceleration is constant, and the time interval, or the time duration the object move. Okay, so this is equation number 4, and equation number 5. Here we express the final velocity in terms of the initial velocity, the acceleration, and the displacement. You can see that in this expression, there is no t or no time involved. So this equation is useful when we don't want to we do not need the time. And if we want to describe the velocity as a function of the position, so this is useful. And this is a special case when the acceleration is 0. When the acceleration is 0, we can have that the velocity is a constant. The velocity is a constant, and distance is a linear function of time. This is a case when the acceleration is 0. Okay, and this is a summary. This is a summary of the kinetic equation. Okay. The interesting point is that can we derive these kinetic equations using the calculus technique, and I will show you how to do that. Okay. Now we will discuss the kinetic equation from calculus. Okay. We will start from the definition of the acceleration. Okay. A is equal to the dv by dt, and now we consider only the case when the acceleration is a constant. So from this definition we have that right, dv is equal to the a dt. This expression is look like that we move dt from the right to the left in the first equation, but this is not exactly at that. This is mathematically we have to say that we write this equation in the differential form. Okay, so we have this differential form of the equation, and if we want to know the velocity, we do the integration to both sides. And if we do the integration from the vi to vf of dv, we to TF of A dt, and in this case, in our case now, A is a constant, so we can move A outside the integration. So we have this equal to the A integral of dt from Ti to Tf, which equal to A Tf minus Ti, and if we use the notation that Tf is equal to T and Ti is equal to 0, we will have this equal to At. Okay, so we have that this Vf minus Vi is equal to At. Okay, so we may write Vf as V at time t, so we have Vt is equal to Vi plus At, and we can take this Vi as a constant, which means that Vi is not dependent on time. It is only Vf that depends on time. Next, once we have Vt, we can continue from the definition of Vt. Vt is equal to dx by dt, and we have that is equal to Vi plus At. So again, we may write this in the differential form as dx is equal to the Vi plus At times dt. So if we want to calculate the position, we can do that by do the integration. Okay, xi integration from xi to xf of dx is equal to the integration from Ti to Tf of Vi plus At dt.